Hello, in this video I'm going to give a recap on stationary waves, otherwise known as standing waves. So we got a change here from what we've been discussing so far in waves, where up until now we've just been looking at progressive waves. Now in progressive waves or travelling waves, this is where we've got a transfer of energy through space. So we've had a disturbance. That disturbance is an oscillation that then propagates through space. It transfers energy, but it doesn't transfer matter. Now in stationary waves it's different because we're not getting that transfer of energy. We're getting energy trapped in space. And this is because we've got a stationary wave is a resultant wave due to stable interference between more than one wave source. Now we're going to be looking at initially at strings and air columns. This is essentially the foundation of musical instruments. So we're looking at stationary waves from a musical point of view. And we're going to be having two waves, an initial progressive wave, an initial travelling wave, which is then reflected. So we're going to have an incident wave in some fashion, whether it's a sound wave in air or some oscillation on a string. And that's going to be propagating through space. It's then going to reflect from some boundary, and the reflected wave and the incident wave are going to interfere with each other. That interference is going to create a stable interference pattern where the resultant wave is no longer going to be propagating through space. Instead, it's going to trap energy. As I say, this is the foundation of musical instruments. Whether it's woodwind or string instruments or brass instruments, you're setting up these stable interference patterns. And the reason that's useful for musical instruments is because you're creating a coordinated oscillation, as we'll see when I put up some animations in a minute. And that coordinated oscillation means that you can then create a coordinated, harmonized sound wave in the neighboring air. So I'm going to use another animation that was created by Dan Russell, the professor who works at Pennsylvania State University. I used his animations in a previous video. But before I bring that up, let's consider the things that we want to be looking at in this particular animation. So it's going to start off, this is going to be looking at a wave traveling along a string, essentially. So this wave is going to be moving from left to right. It's going to hit a fixed point, and then it's going to reflect. So we want to see how this wave is traveling towards, as a progressive wave, a single progressive wave, traveling towards this boundary, this fixed point is going to reflect off of. And then when it starts to reflect, we're going to see a number of things change. First of all, we're going to see the amplitude increase of the maximum displacement of the oscillation is going to increase. It's going to double, because we're going to get some parts of the interference pattern are going to be constructive interference. So we're going to get the incident wave and the reflective wave adding up. When they're adding up in phase, we're going to get the constructive interference, which is going to increase the amplitude of the oscillation. We're also going to see some fixed points on the stationary wave, the resultant wave, which don't move. So we're going to have these fixed points that aren't oscillating at all. These are called nodes. And in between these fixed points, which are going to be evenly spaced, these nodes are caused by the destructive interference. When the incident and reflected waves are in antiphase, you're going to get these nodes. In between the nodes, we're going to have the larger amplitude oscillations there. These are going to be our antinodes, where you've got the largest oscillation, the greatest amplitude. So, and we're going to see these things oscillating up and down. We will now see, once the standing wave has been set up, that there is no movement left to right. That's all disappeared. The oscillation is now going to be coordinated, that everything between two nodes is going to be moving completely in phase. So it's going to be moving up and down in phase, all of the points. Okay, you're going to have differences in the amplitude and the displacement, but you're not going to get a difference in phase. So if we've got our standing wave, which is set up with that profile, all of this will be moving down in phase. On the other side of the node, it'll all be moving up in phase. So between two nodes, everything's in phase. For either side of a node, they're going to be in antiphase. So we've got very different properties here between the initial progressive wave and then the resultant stationary wave. So I'll bring up the animation and then we can look at for all of these different features. Right, so here's our flat string. Here's the progressive wave coming in with a relatively low amplitude. It reflects from the end. The amplitude now doubles, and we can now see that there isn't a left-right travel anymore going on here. All of the energy is trapped. We've got these fixed points that then set up. Right, I'll let it play through again because this animation repeats. It doesn't just keep on going on forever. There we got a fixed point here. You can see there's no oscillation there. That's a node. We got another node. We got another node. So you can see all these nodes. You can see the much higher oscillation with these antinodes that it run through again, where everything is in phase between these two nodes here with much greater amplitude. So you can see there how that stationary wave is being constructed. Now we can't just have any old setup in order to create a stable interference pattern. So let's look at strings then. Let's go to our musical instruments. We'll take strings. So we've got a string which is held in place between these two fixed points. Now these two fixed points are going to have to be nodes because, well, nothing can move here on the string. They are fixed in space. There's going to be no oscillation, so they're going to have to be nodes. If we want to set up a stationary wave on this string, there is necessarily going to be some kind of consistent relationship between the frequency of oscillation of the wave and the length of the string. So let's have a look at this. So the simplest way we can set this up is these two nodes are adjacent nodes. So we draw in our wave profile like this. So this is the maximum positive upwards displacement that we're going to get on the string at a particular point. Draw in the dotted line to show where it would be at the negative of this once it's gone halfway through its oscillation. So this is our wave envelope. We've got two adjacent nodes here, and this is the simplest, the longest wavelength standing wave that we can set up. So this is denoted with F0. This is our fundamental frequency of oscillation. Now we can see with this that there must be this relationship. If the length, the distance between these nodes is L, then we can say that the wavelength here is going to be 2L. You know, we can see we got half a wavelength that we've drawn out here. So our wavelength is going to be equal to 2L. So we've got this relationship between wavelength or the frequency, because in this case, along a particular string, the speed of propagation isn't going to be changing. You know, for a particular string, our V is going to depend upon things like the tension in the string, which is going to depend on the mass and things like that, our mass per unit length. So V isn't changing. We've got then this direct relationship between then the wavelength and the frequency. So here we've got a wavelength of 2L. Let's set up then the next simplest situation for this standing wave. So we're going to stick in another node in the middle. So now we've got three nodes. We just added another node in. So we'd go up, we'll go down through this node and then back to the other node. So we've now got this sort of standing wave. Here we've now got one full wavelength. So our wavelength is now L. So we've halved the wavelength. So we must be doubling the frequency. So we've got 2F0. Now if we move to the next one, we're going to have 4 nodes on this. So up, down, A little bit wonky, but I'm trying to draw these out a little bit quicker now. Now we've got this one. We can see that we've now got that our wavelength is going to be 2/3 of L, which means that we've now got 3 times the fundamental frequency. So we end up getting this relationship between the frequency or the wavelength, whichever one you want to look at, and then the distance between the nodes, the length of the string before it's been stretched, before it's been plucked, and we've created these oscillations. So you've got certain frequencies of oscillation for a particular length of string. Yeah, this is what people are playing around with when they're using their fingers on a stringed instrument. They're changing the string length, they're changing these wavelengths, and then because we've got this coordinated motion where everything here between these nodes is all moving in phase, we've got this nice coordination here. Is going to create a nice coordinated wave in the air which is surrounding the string. So that's how we're building up our different frequencies, our different standing waves on strings. We got a similar thing on air columns. Now we're going to have 2 different types of air column. We're going to have ones which are closed at one end and open at the other end, and then we're going to have some which are open at both ends. Now I'm going to have to draw these a little bit smaller. So if you've got a closed end, that's going to have to be a node. If you've got an open end, it's going to be an antinode. Right, so let's draw these in. So we're going from antinode to node. That's our simplest, that's our fundamental frequency. That is 1/4 of a wavelength. So our wavelength is going to be equal to 4 times the length of the tube, if the tube length is L. Right, then we can add in another node or antinode. Well, in fact, it's going to be both. So we've still got our node at the closed end of the tube. Now we're going to want to have another node which is sitting in here as well. So let's put another node there. And then our next arrangement is going to look something like that. So here we've now got, well, we got 3/4 of a wavelength has been drawn in here. We haven't quite made it all the way around. So we've got 3/4 of a wavelength. So our wavelength is going to be 4L/3. If we've reduced our wavelength by 3, then we've increased our frequency by 3. So that's gone up 3 times. And we can keep extending this on as well in the same pattern, in the same sort of sequence. So the next one that we're going to have is going to be, I'm not going to be getting all of these in, am I? Yeah, it's going to end up looking like that. So we're just adding in more nodes, exactly the same as we did on the string. If we've got open at both ends, and I'll come back to, I know we've got an open end here, we're going to have 2 open ends, which is maybe a little bit counterintuitive, so I'll get onto that in a minute. Here, if they're open at both ends, then we have to have an antinode at both ends, so that's going to be our simplest setup. We've got a node in the middle, antinode at both ends. So that is half of a wavelength. That's our F0. We've got half a wavelength. So our wavelength is equal to 2L. When we go to the next setup, then we're going to get a full wavelength in. So we're going to go down to the bottom and back up again. So that is now a lambda is equal to L, which means we've doubled the frequency. So it's quite easy to draw these things out. We're just adding in more nodes each time. You know, we started off here, we've got 2 nodes, 3 nodes, 4 nodes. Here we've got 1 node, 2 nodes, 3 nodes. Here we've got 1 node, 2 nodes. So it's just building up in that way when you're drawing these things out. And then it's quite easy to work out how the frequencies are changing. You know, these ones are just doubling up each time, or we're just multiplying. We've got fundamental frequency, 2 lots, 3 lots, much the same as we got here. Then we got this one is just going up slightly differently when we've got an open end and a closed end. Now you might be wondering, with all this discussion of air columns, how we're getting a reflection from an open end of a tube. Because remember, with all these standing waves, in order for them to be set up, we've got waves just bouncing backwards and forwards along the length of these things. So it's quite easy to see when you've got a string, wave goes along, hits the end of the string, reflects, goes back, and then, vice versa. Every time you've got one of these fixed points, it's just bouncing back on itself. Now, if we're setting up a stationary wave in an air column, we got a similar thing happening where the sound wave is then reflecting from both ends. So, and that's actually something as well, which is well worth remembering before I continue with this point about open ends of tubes. Although we're drawing out these wave profiles here for these sound waves, our waves in an air column, you've got to recall that these are all longitudinal waves. So don't get caught, as a lot of people do, of thinking that the particles are oscillating up and down as we look at it on this screen inside the air column. Of course, everything is oscillating up and down the air column. This is the issue that people can quite often forget, as I pointed out in the previous videos, that when we're drawing these wave profiles of longitudinal waves, it can be easy to start thinking about them as transverse waves when they are not. All of these particles, if they're moving, i.e. if they're not at a node, are moving up and down the length of the column. So how do we get a reflection at the open end? I mean, that just seems blinking weird that can possibly happen. I mean, there's nothing there. There isn't a boundary. So what's going on with that? Well, I'll go back on the previous screen because we've got a bit more space to draw on here. So you've got your air column like this. So say it was open at both ends. You've got a wave which heads in one end. So remember, this is for sound waves. We're thinking of these as being pressure bands, essentially. We've got concentrations of particles which are sort of pushed together, and we're getting these bands of pressure as described in my previous videos moving along this tube here. So we've got high pressure, low pressure in these bands all moving along. Remember, all of the oscillations are going from left to right. The wave is propagating here from left to right. So what happens then when it reaches the outside of the tube? So remember, this high pressure and low pressure is relative to the general pressure, which is outside everywhere else. The outside of the tube isn't affected by what's going on inside the tube. Not until, at least, the wave then emerges from the tube. Eventually, we're going to get this high pressure region is hitting the end of the tube. That then comes out of the tube, this high pressure. It then leaves us with, the next thing we're going to see is the opening of the tube is going to be a low pressure bit. So we've got the high pressure here. The previous high pressure bit has just left. We've now got low pressure there with general pressure on the outside. So we're going to get sort of suction effect where the higher pressure outside the tube is going to force air back into the tube in the opposite direction, into this low pressure region. So that is going to start up the reflected wave, which is going to go the other direction down the tube. So this is going to happen at both ends. So this is how we're getting this reflection at an open end of a tube because of these pressure variations. So yeah, that's what's then happening. That's what you're setting up if you're playing the flute, some other woodwind instrument, whatever it may be. You're setting up these waves, these density, these air pressure waves that are moving down the tube, and you're getting that suction effect, and it's setting up that sort of resonating effect that you're getting up and down the tube as they're reflecting from these open ends or closed ends, depending on what instrument you're playing. Now, this doesn't go on forever. We've been talking about energy being trapped in these standing waves, and yeah, in a completely idealized standing wave, yeah, we've got trapped energy. The energy is trapped between the nodes. There's no escape here. Everything's just moving up and down, and if there are no losses, that will just keep on moving up and down, and it's trapped between these nodes. There's no propagation through space. Now, of course, you get losses. This is all existing inside an atmosphere. This, if it's a string that's going up and down, is pushing the air around. We've got these pressure waves moving along the air column and then out into the wider atmosphere. So we are getting some energy is getting transferred out of the standing wave. I think it's something like 10%. I think it is when they talk about, give or take. It's not going to be an exact figure, but you can think around 10% of the energy in the air column that's vibrating in a musical instrument. About 10% of that comes out as sound and is then transmitted to the surrounding air and then goes off to the people who are listening to the instrument. But you've got 90% of it is just trapped up and down this air column. So and obviously it gets sustained by the person who's playing the instrument. They can keep topping it up. So you still get, as with all of these things, you're not getting these idealized cases where no energy escapes, and just as well, because otherwise we'd never be able to hear anything that was being played on a musical instrument. There are quite a lot of other cases. Stationary waves can get set up in loads of situations. It's not just these musical instruments. There always used to be the case if you drove along the M4 motorway that you'd get on the car radio these peaks and troughs in volume. It'd get really, really loud and then really quiet. And that was because you were traveling between two transmitters. So you had transmitters and these were creating stationary waves along the length of the motorway. If you wanted to be particularly nerdy, you could work out what speed you were traveling at by timing the distance between successive nodes or antinodes. So if you knew how long it had taken, then you could work out, and you knew what frequency you were listening to on the radio, then you could work out how far the car had travelled, how fast you were moving along, or vice versa. You could look at the speed of the car and then try and work out the wavelength of the signal. So, and it was really quite pronounced. It's not something we encounter so much nowadays with your, your digital radios and such like. But with when we were listening to AM radio, it was particularly noticeable. So you come across it in that case as well. And they're nowhere near as confusing as I find a lot of people seem to think they are when they first come across them. When I do tutorials on stationary waves, people have a lot of problems drawing out all of these different frequencies, all of these different harmonics, going from the fundamental frequency and then various higher level harmonics. It can seem more complicated than it actually is. Getting used to this pattern of drawing out, just adding extra nodes in order to go through all of your different harmonics. It's pretty straightforward once you've done it a couple of times. So don't let all of this stuff scare you off what is actually quite a nice self-contained, before you go off to university at least, a nice self-contained and relatively straightforward topic.